Hello, it's Jim from JetsonHacks.com. On today's show, we are looking at running dual CSI cameras on the NVIDIA Jetson Nano Developer Kit, version B01. Recently, NVIDIA updated the Jetson Nano carrier board to version B01. This included support for 2 CSI cameras. Today I want to share with you how to access those cameras. Then we'll go over some optimization strategies for incorporating them into your OpenCV applications. Here are the 2 Raspberry Pi version 2.1 cameras that we are going to install. Notice the end of the ribbon cable connector. One side has blue tape, the other side has the contacts. The contacts will go towards the Jetson module when we install it. There are 2 camera connectors here for the CSI cameras. Gently pry up the plastic camera cable retaining clip, as shown in the picture. You can use your fingers or a small screwdriver. Just remember to be gentle. Next, insert the camera cable ribbon. Make sure that the tape side is facing towards the outer edge of the board. Also, make sure that the cable ribbon seats all the way into the connector. Press down on both sides of the camera cable retaining clip to capture the camera ribbon cable. It will look something like this when you're finished. Repeat the process for the other camera, and you're ready to go. I'm using the helping hands from a solder station to help me with my demo. On the JetsonHacks Nano account on GitHub, there is a repository named CSI-Camera. Let's clone that repository. Grab that repository's address, then git clone. Now let's switch over to that repository's directory. Okay, with that out of the way, let's test our cameras. Here's a simple GStreamer command. This sensor ID parameter tells us which camera to choose. We have 2, so it can be 0 or 1. Let's test out camera 0. Yikes, that's scary. Close that up. No one wants to see that. And let's test out the other camera. Let's try out old number 1. That's scary too. Okay, if you're still here, both cameras appear to work. Before we go any further, notice that it prints out the sensor modes. Let's put those sensor modes into a file. Just grab them here. Let's call it camerawork.txt. You can see that there are 5 different camera modes. They range from 3264 by 2464, frame rate of 21, up to or down to, depending on how you look at it, 1280 by 720, 120 frames per second. So we'll keep that around. That will be useful later. We will be running OpenCV examples in Python 3 today. In order to run OpenCV in Python, we will need to install NumPy. Let's do that. Okay, now we are ready to install NumPy. Let's install Python first. NumPy. Okay, installation complete. Let's open up Visual Studio. We are going to use that as our Python IDE. Let's open up our repository directory. Let's run simplecamera.py. Oh, so that appears to work. It appears to be lagged also. One of the things we're going to talk about in this video is how to kind of get your frame rates up. I don't know which camera to look at again. It's always a problem. Let's close this one up. We also have dual camera. So let's take a look at both cameras at once. We'll run that example. Okay. So here's the two CSI cameras. One of the things I find interesting here is that even though the two CSI cameras are the same, they're two separate cameras, but they're the same make, you get different color characteristics out of them. You can see down here, the webcam that's connected to the Nano is very saturated. And then the CSI cameras are less so, but there's still quite a bit of color difference between the two CSI cameras. So each camera has its kind of own little variation that you have to take into account. Now, if you're just looking on how to access the cameras in your program, all you have to know is the sensor_ID in NVArgus in the GStreamer pipeline. The Jetsons use GStreamer as their access to the cameras. As mentioned before, the sensor ID parameter to NVArgus camera source is the key to this. There are other parameters here you may find useful. You can request a width of a frame, a height of a frame. You can also request a frame rate. You can also request a sensor mode. Let's pull up our sensor modes again. So here's our sensor modes. This is kind of a shortcut here. You can request any of these 5. The numbering starts at 0. So 0, 1, 2, 3, 4. If you don't request a specific sensor mode, it will try to configure it based on the parameters that you passed. And then we construct the rest of the GStreamer pipeline. Then we end up here with app sync. This tells GStreamer that an application program is accessing the GStreamer pipeline. Of course, this is all set up for Python. You'll have to translate it into whatever program language you're using. Here are the default sensor modes that we use in this particular case. In this case, we take a capture width and a capture height, which is requesting the frame size from the camera. And then we convert that to this display width and display height by using a video convert. In our case, we're going to use sensor mode 3, 1280 by 720. Please return it in 1280 by 720 at 30 frames a second. So let's go back over to simplecamera.py. There's an equivalent statement here. If we look at the sensor modes, the sensor mode 1280 by 720 can be provided in 60 frames per second here, or 120 frames per second. In our case, we request 60. And the program itself is pretty simple. Basically, in OpenCV, we set up a video capture. We set up a window. We read a frame from the camera, and then we show a frame from the camera. And then in the third part here, this is a little tricky. The wait key is basically a processor yield. It will wait up to 30 milliseconds. And if it gets a key back, it looks to see if it's equivalent to 27, which is the escape key. This can act as a frame rate limiter in this type of loop. So you'll always have a 30 millisecond wait in your loop. It's important in your main input loops to have some type of processor yield. It allows the operating system to multitask. 30 is rather an arbitrary number. Typically, the results of this are around 30 frames per second. Let's set it to 5. And let's run it. Make sure to save it. So we see that it lags a little bit here. It doesn't really sync too much with my voice. It appears to be about the same as the webcam. A little bit laggy. Now we can start guessing why that may be, but because it's not instrumented, we don't really know. One of the reasons may be that we're requesting 60 frames a second from the camera, and it can't display it that fast. So let's change that. We'll set the frame rate to 30. There's no underscore. And now it's correct. Still, it's a little hard to tell. I don't know which camera we're looking again. So even though it's correct now, we may want to actually instrument this program, tell us where the time is being spent when we are executing it. It's not good form to have to try to guess through everything. We'd also like to know how many frames are being displayed a second. So in the next part of this video, we'll kind of go over some general strategies for doing that. Let's close this up. We'll go over here to Instrumented. I've written a class to help us with this. It's called Timer. It uses some Python voodoo. I just wanted you to know it's here rather than kind of go step by step through what it does. Basically what this class does is it provides a wrapper around a block of code that we're going to execute and runs a timer on it. I won't go into the details here. You can read through the code. It's simple, but it's kind of warped. So let's go look at simplecamera.py in an instrumented mode. This is the same program as before, except it has been instrumented. So we take our time context class and import timer. Then you can see that we instrumented this block of code. Here's how we might read this code. We start a timer. We will call it context_time. We'll read a frame from the capture device, and we will print out the time that has elapsed since we started the timer. Next, we show the frame that we captured on the window called CSI Camera. We print out the elapsed time from when the timer started, and then we are going to wait, in this case, 20 milliseconds for a key. We'll print out the elapsed time since the timer started again, and then we'll print this as a marker. So let's run this, see what happens. Camera's running. You can see that all the instrumentation down here is coming out. You can see that it's pretty messed up as far as the display. Let's kill this. So we can see down here, we enter the context. This is all in seconds here. 3 milliseconds, 6 milliseconds, and then it waits to 20, and that gives us a cumulative of almost 27 and a half. So each frame takes about 28 milliseconds here. You can see that that number actually varies across frames. Here's 23 milliseconds, 28 milliseconds, and so forth. You can see the problem. The camera is producing 60 frames a second. You're only displaying 40 of them. In most implementations, the cameras are buffered, so you're just falling behind as time goes by. Now, of course, we can cut down this wait time. Let's cut it down to 5. Try that out. You still have some type of lag here. Let's close that. So this is pretty close. You're getting down to, looks like 15 milliseconds or so. But you get these stutters occasionally of, here's a 24, 28. So you never quite keep up with it. So let's change the frame rate to 30. Let's run it now. And now it works correctly. So that runs a little counterintuitive. You would think that if you crank up the frame rate on the camera, that it would actually display faster. It doesn't. It's limited by the amount of time that it takes to actually display it and read from the camera. This is with one camera. Let's switch over to dual cameras. This is kind of the naive implementation. We take simple camera and basically just double the video capture pipeline. We set it up as left cap and right cap. We use our frame rate of 30. This one's instrumented also. We set up our timer as before. We capture the left image, and then we capture the right image. We combine the images into one, a left image and a right image. This is Python speak for combining the two images. And then we show that. Then we are going to wait our 20 milliseconds as before. And then we're going to break out of this if we hit the escape key. So let's run this one. This has some interesting behavior. The left and the right do not appear anywhere near synchronized. Let's close this up. Let's uncomment our elapsed times and run it again. Save and run. Let's take a look at some of our numbers here. We have 33 milliseconds, 34 milliseconds, 40, 46, 64. You can see that our numbers kind of vary quite a bit here. In this particular case, it doesn't take very long to read the cameras, but to actually combine the images and to show them. Here's a 28, 5, 28 to 5. You can see it's rather inconsistent. 10, 9. So it's a little choppy. It can go anywhere from, it looks like 25 milliseconds to 7 or so. You have to subtract the time to actually read the frames. I'm not really nodding back and forth. I'm looking back and forth on the screen. It appears that I'm nodding. No, no, no. One thing that might be useful is to actually figure out how many frames per second are being displayed. So one insight that I've shared with you already is to pick your frame size judiciously. That seems kind of obvious. The second one isn't quite as obvious. We've been talking about these as sequential operations. Here's how we think about this program. We read a frame, we manipulate the frame, we display the frame, and then we wait a little bit. This is all done sequentially. As you know, the Jetsons have more than one CPU on them. One of the key ideas here is to take part of this loop and execute it on a different CPU. For example, we may want to take the frame reads and put them in a separate process that we can run on a different CPU. Now we can split this up to some degree. We can read the frames on a separate process. One of the caveats of all this is that you have to do GUI manipulation on the main thread. The main thread is the thread that you call up when you start your program. So in this case, this is the main thread that we're looking at. What we are going to do next is set up our frame reads in a separate thread. Oh boy, Let's close this one up. Now let's open up dual camera _FPS. One of the features we'll add here is the number of frames per second that are being displayed. Let's look at setting up our cameras. It's in a separate class. It's here in the CSI Camera. We will use the Python threading module. We'll use a repeat timer. That will help us with setting up our frames per second. And we'll set up a class. It's called CSI Camera. When we instantiate a instance, we call this. All of these are instance variables. Typically, we just initialize them to null. And then we have some instance methods here. The instance variable video capture holds the OpenCV video capture. You can see that you pass it a GStreamer pipeline, as we've discussed before. And it does the first read to start the capture. Now here's where it starts to differ a little bit from the previous versions. Now, when we start the CSI camera, we call this particular instance method. And the key component here is that we create this new thread. The target of the thread is update camera. That's another instance method. Update cameras down here. We'll go through that in a second. And then we start the thread. Basically, that starts up the thread on a different CPU if available. It uses the underlying OS kernel pthreads, I believe. Next instance method is stop, which will stop the thread. And running in the thread is this instance method. It does a couple of things. It basically reads from the video capture device. And then a tricky bit, it's kind of beyond the scope of this video, but you basically put a read lock on here so that you can synchronize between processes. We save the frame that we just read in the instance variable frame, and we increment the number of frames read by 1. Now, when someone goes to read our frame, we basically make a copy of the frame and hand it back to them. That's what this does. And then here's the kill method, release. We also keep track of the number of frames that have been displayed. That allows another process to tell us that it's displayed something. And then we have down here the familiar create GStreamer pipeline. So we've encapsulated the camera as a class. So let's go over to dual camera _FPS and try this out. So we basically read in our CSI camera class. Here's a function to draw a label on a CV image. Here's a function to read the camera. We read our camera image into this variable. And then on top of that, we draw the number of frames that have been displayed and the number of frames read. Here's some constants for when we want to play around with the size. In this next function, we create the cameras. So left camera, sensor ID is 0, sensor mode is 720, which is 1280 by 720. Frame rate of 30, display height and display width. That was 960 by 540. Same thing with the right camera. We also start the cameras here after opening them. We create the CSI camera window. A small sanity check to make sure that the camera's opened. Then here's our main block again. We read the left image, the right image, we combine them into one image, and then we show them. And we tell the FPS counter on the camera to increment by 1 after we do the display. So let's try that out. Ooh, that looks good. You can see now that they are synced. You can see that they're faster than the webcam is. We are getting 35 frames per second displayed, and we are reading 30. So let's crank that up and see what happens. Let's close this. Notice in our call to wait, we specify 20 milliseconds. So we would expect to see 50 frames per second in best case. Why aren't we getting somewhere near that? Sensor mode is 720, which is 1280 by 720. And then our display height and width is 960 by 540. There's a transformation that has to happen between the frame size and the display size. We notice that isn't an even divisor into 1280 by 720. Let's comment this out and switch over to 640 by 360. Basically quarter size of 720p. Save. And let's run it again. And we picked up a few frames per second. We're up in the 40s. Let's try cranking up the number of frames that we read. Let's go to 60. We'll do that on both cameras. Now we're reading 60 frames a second. It looks pretty good on the screen, but we are only showing 39 frames per second. While we are here, let's update our sleep time. We'll make that 5 instead of 20. Most we would expect is 200 frames a second at this point. Let's save that. Let's run it and see what happens. Okay, so we can see that we're reading 60 frames a second, and our frames displayed is 78. That's pretty good. So again, you can see by picking your frame rates and your display size, you can adjust the frames per second being shown. In general, it's computationally less expensive to use evenly divisible multiples of the frame sizes here for display. Okay, that leads us back over to our face detect example. Let's close this up. Let's start clearing some stuff off. Let's open up our face detect example. Let's go through the code a little bit here. Here's the face detect method. We are going to use frontal face, HAR cascade for it, and an eye HAR cascade. Open up a window. Start counting our FPSs. We're going to use our timer so we can measure how long each one of these things takes and print it all out. Let's run it and see what happens. So the camera shows up. You can see it's pretty slow. Let's close that up. So we'll just take an example out of here. It doesn't take very long to actually read the camera. It takes a relatively long time to detect the face. So you would expect 4 or 5 frames per second. 17, 15, 16. Maybe 6 frames a second. Let's look and see what camera mode we were using. So 3280 by 2464. And our display width was 820 by 616. Frame rate of 21. So we were going full frame on that. Let's go over to the faster example. We are going to use our CSI Camera trick. We will display the frames per second on the image. 640 by 360 is our display size. We're using sensor mode 720, frame rate of 30. We cranked down the sleep to 5 from 20. Let's see what we get out of that, baby. So that about doubled or tripled our actual frame rates. 9, 10, somewhere in there. I wonder what happens when you change the frame rates. Let's crank it to 60. As you would expect, it's frame limited. So it runs the exact same speed, hopefully. It should. One of the interesting things here is that the model is trained for full-on frontal recognition of the face. When I'm looking directly at the camera, you get pretty good recognition. As soon as I go off axis, it doesn't recognize you. Of course, this works on images also. Well, it's pretty good. The man here is a little bit off axis, so it has difficulties with it. You have to remember another thing about this is that it's very dependent on the lighting. If you have poor lighting, it doesn't work quite as well. Just some examples. Let's close this up. And then the third trick of vision processing is to use as small of image as you can to get higher frame rates. Let's cut this in half again. Now you can see that we're getting 30 frames a second. And this is a major trick of computer vision and most machine learning methods. You try to use as small a frame as possible to reduce the computing time. Hey, if you like the video, give it a thumbs up. And if you have not already, please subscribe. Obligatory sign off. Stay safe. I don't know what that means, but everyone says it now. Thanks for watching.